Ever wondered how your phone vibrates? Or how an electric car just glides down the street almost silently? Well, it's not magic. It's physics. And today, we're going to pull back the curtain on the simple, brilliant science that turns invisible electricity into the very motion that powers our world.
I mean, think about it. Every single day, you're basically a wizard. You press a button, your car unlocks. You flick a switch, a fan starts to spin. With just a simple touch, you're harnessing one of the most fundamental forces in nature and telling it what to do. The real question is, how?
Right? How does a bunch of electrons flowing through a wire translate into the very real physical movement of a lock or a fan blade? What's the secret connection between electricity and motion? Well, that's exactly what we're going to break down today.
And the crazy part is, the answer is literally all around us, hiding in plain sight in the tech we use every single day. Believe it or not, the same basic idea that makes your car door lock clunk is also what used to spin the disk in an old DVD drive. It all comes down to a hidden property of electricity, and our story starts with a single groundbreaking discovery.
This discovery revealed something profound, a deep, inseparable link between electricity and magnetism. As it turns out, they're really just two sides of the same coin. And this whole revolution in thinking, it all kicked off with a surprisingly simple observation. So a guy named André-Marie Ampère noticed something kind of weird. If you take two parallel wires and run an electric current through them, but in opposite directions, the wires will actually physically push each other apart. This was a huge deal because it was the first real proof that electricity could create a tangible mechanical force. It's because any wire with a current flowing through it generates its own magnetic field, and when you put two of these fields next to each other, they can push and pull.
Okay, so a straight wire can create a little magnetic push. But let's be honest, a tiny push isn't going to change the world. So the next challenge was, how do we amplify that force? How do we make it powerful enough to actually be useful?
The solution was almost elegant in its simplicity. Just bend the wire into a loop. You see, when you do that, all the magnetic field lines inside the loop suddenly get organized and start pointing in the same direction. This concentrates the magnetic field right in the center, making it way stronger and much more focused. And hey, why stop at just one loop? If you coil that wire into a tight spiral, you create what's called a solenoid. Now, every single loop adds its magnetic field to the one next to it, reinforcing it and creating this incredibly powerful, concentrated force. This simple coil is the heart of so many devices we use today. And this is where the big aha moment happens. If you look at the magnetic field coming from that solenoid with the current running through it, it looks identical to the field from a classic permanent bar magnet. We've literally created a magnet just by running electricity through a wire. This is the birth of the electromagnet.
Now here's the real game changer. Unlike that regular old bar magnet that's always on, you can turn an electromagnet on and off with a simple switch. Cut the current, the magnet disappears. Turn it on, it's back. That control, that on-off ability, is the secret ingredient to so much of our modern world.
So how do engineers know which end of their new magnet is going to be north and which end is south? Well, they use this brilliantly simple trick called the right-hand rule. It's a quick and dirty way to figure out the direction of the magnetic field without any complicated math. And it's super easy to remember. You just wrap the fingers of your right hand around the coil, pointing them in the same direction the current is flowing. When you do that, your thumb will automatically point to the north pole of your new magnet. Fingers follow current, thumb points north. Simple, effective, genius. All right, so we've built a magnet we can turn on and off. That's a pretty cool party trick, but what's it actually good for? Well, it turns out this simple invention is the hidden powerhouse behind countless things we use every single day. Let's take a look.
Seriously, these things are everywhere. That solid thunk you hear when you unlock your car door, that's a solenoid. The deep rumble from a subwoofer, solenoid. They're in pinball machines, medical equipment, automatic transmissions. These little on-demand magnets are some of the hardest-working unsung heroes in technology.
The classic school bell is just a fantastic example of clever engineering. So you press the button, the solenoid turns into a magnet, and it yanks that little metal arm over to strike the bell. But, and here's the brilliant part, that same movement pulls the arm away from the electrical contact, which breaks the circuit. The magnet instantly turns off, the arm springs back, touches the contact again, and the whole cycle repeats itself over and over, making that continuous ringing sound. How cool is that? A simple push or pull is useful, for sure, but the real holy grail of motion is continuous rotation.
The world truly changed when engineers figured out how to take the solenoid's simple linear push and turn it into a relentless spinning force. This is the story of the DC motor.
The problem was a big one. How do you take a momentary magnetic push and make it, well, not momentary? How do you design a machine that keeps pushing in the same direction over and over again to create smooth, powerful rotation?
The answer was the DC motor. It's built on the same principle, an electromagnet pushing against another magnet. But it has one extra brilliant twist, a clever little switch that flips the current at just the right moment. And that one addition is what makes the whole thing spin continuously.
And this is the heart of the whole operation, the split ring commutator. I mean, it looks so simple, right? It's just a metal ring with a gap in it. But this little thing is the key to everything. As the motor's coil spins, this ring flips the direction of the electric current every half turn. That simple act is what keeps the motor going and going and going.
Okay, so let's walk through it. First, the current flows, which turns the coil into an electromagnet, and the magnetic forces give it a push, so it starts to rotate. It spins until it gets to that gap in the commutator. For a split second, there's no current, but its own inertia keeps it going. Right as it crosses the gap, the commutator reverses the current. This flips the coil's magnetic poles, and this is the magic part. That flip means the magnetic forces now push it again, but in the exact same rotational direction as before. This push, flip happens over and over, super fast, creating one smooth, continuous spin.
So that one brilliant little invention, the split-ring commutator, didn't just create a new gadget. It fundamentally built the modern world. Let's take a quick look at just how much of our lives are powered by this simple device.
I mean, just look around you. The fan that's cooling your computer, the blender in your kitchen, that power drill in the garage, all powered by DC motors. Even the quiet, powerful motors in electric cars are just a more advanced version of this same core idea. It's the unsung hero of our technological age.
Of course, the design has gotten way more sophisticated over the years. Modern motors use lots of coils and a more complex commutator. This just makes sure there's always a coil in the perfect spot to get the maximum magnetic push, which results in way smoother power, more efficiency, and incredible reliability. So from a simple push between two wires to a planet powered by spinning motors, it's an incredible story of human curiosity. We learned how to command an invisible force, and by doing that, we built the world we live in today. And it really makes you wonder, what other invisible forces are out there, just waiting for us to figure them out, and what new worlds will we build then?